today we're going to do our our second proof packet. It's on congruent triangles, and there's a lot of information to know. Okay? So, the first things are the congruency theorems for triangles. And that means that if I see two triangles are congruent, for example, keeping in mind I'm drawing them freehand, if a side is congruent to what we call a corresponding side, and the second one is also, and the third one, we call that side, side, side congruency theorem. That assures us that if I could pick this thing up and put it on top of this other one, everything would coincide. Okay, now side, angle, side. This one's pretty easy because we're just looking at the sides. This one is important that the angle is in between the two sides. Use my same little generic triangle. So if I mark these two sides congruent, I need the angle and then the next side. So it's side, angle, side. I can't skip something, so I couldn't go like side, skip all this, side. Okay? So you want to start. Sometimes it's hard to realize where you should start. If you start with something that isn't marked, so if I started with this angle that's not marked, and I travel along the next thing that is marked, I get side, then angle, then side. If I had started with this one, I would have side, angle, side. So the angle is in between or formed by those two sides. Angle, side, angle. Angle, side, angle. So now it's the side that's in between. Get those congruency symbols. It's important to say congruency after it because we will be learning similarity, and that would be a different property. So the side is now in between the two angles. Again, I'll start with something that's not marked. If I start with the angle, I also don't have a side that's marked. You can have more than two things missing. So I would go over to here and say angle, side, angle. Again, the important thing is the side is in between the two angles. Angle, angle, side, our last one. Angle, angle, side, angle, oops, angle, side. So if I start with one that is missing, I have side, angle, angle, and that's okay, I can say it backward. Or if I started here, I'd go across the side that's not marked, and I'd have angle, angle, side. Now we never use angle, 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 or side, side, angle. And that's because we aren't guaranteed to have triangles that are equal in size. You know, we can't put one on top of the other and have everything coincide. So this triangle is an equilateral triangle, and so is this one. All their angles are equal, but you can see they're not the same size. I would have to reduce it down. That's called a dilation. You'll learn later, for this to be true. The other one is side-side angle. That one is also not true. So I have an angle, a side, and I'm showing you these two sides have the same length, but I could make this triangle with angle, side, side, and if we took this off, I could make that triangle with the same side. So there are two possible ones I could get using side-side angle. So these will never be congruency theorems. And let me put congruency here also. Okay, so we learned last time how to start out our proofs, and we learned algebraic proofs. Now we're going to go to geometry proofs. So you're always going to mark the figure with the information given, and then you're going to look at the figure and do vertical angles are equal or reflexive. Almost in most proofs, not all, but most, you'll find one of these two. So let's talk a minute about that. Vertical angles are angles formed by two crossed lines. Okay? I call them a butterfly. So it's this and this. And so you see the butterfly wings? There's the little body. Okay? So vertical angles are formed by two straight lines crossing, and they're across from each other. Now, these two here are also vertical angles. And vertical angles are always congruent angles. The other one we learned last time, which was reflexive, and we learned it as an algebraic thing if you have, x equals x. That would be the property. For reflexive in a geometry proof, it's going to be when we say that line is equal to itself. It's a side in this triangle, and it's a side in that triangle. So we say that's reflexive. We'll say that's congruent to itself. Okay? Some other ones. So we're going to go heavy on the theorems first, and then we'll work them. A midpoint creates two congruent segments. Okay, some people call this, or some books call it, definition of a midpoint. I like to use the actual thing it is because you tend to remember it better. Okay? So a midpoint creates two congruent segments. So if I have a segment, it's wobbly, and I have something, I have the midpoint right here. Now I purposely drew it, so this is a midpoint of that. It doesn't mean it cuts this in half. It doesn't go all through. It's only the segment that it's the midpoint of that is getting cut in half. A segment bisector creates two congruent segments. This is an example of that. This line, let's call this line L. It's a segment bisector, but it is not being bisected. So it's cutting this segment into two equal parts, and you'll see that in our proof. And in an angle bisector, the same thing. The angle bisector will create two congruent angles, right? We can hold this until we get to a perpendicular one, and then we'll talk about that. So let's go to this proof, our first one. And it says, okay, we are given. So we're numbering our proof just like before. BC is congruent to DC, and AC bisects angle BCD, and that is given. So remember how I told you we want to mark our diagram? So BC, this segment, is congruent to DC, that segment. I mark it, and I've already said it, so I don't need to repeat it. The next one, AC bisects BCD. Now I'm going to use what I know a bisector does. It forms two congruent angles. So I'm going to mark this one and this one congruent to each other, and I'm going to write that down. So number 2, I'm going to say angle BCA is congruent to angle DCA. Watch the corresponding points. B corresponds to D. And that is because an angle bisector creates two congruent angles. So I'm getting that directly from this word. When I see bisects, I apply what a bisector does. But now I'm out of room. I'm out of information. I have nothing more. That's when I look for these. Okay? So I don't see vertical angles in here. Come on in. What I do see is reflective. So that is reflexive property. That's where I'm going to use those. So over here, number 3, I'm going to say AC is congruent to AC, and that is my reflexive property of equality. So now I want to look at it and see, do I have enough? Do I have one of my congruency theorems? So I'm looking at my figure, and remember, start with something that's not marked. Maybe this one? I could start here, I could start here. So if I start here, I'm going to go along, and it's side, angle, side. So that's my congruency theorem. Side, angle, side, congruency. And I'm going to put what I wanted to prove, that the two triangles were congruent. And then I put the steps where I mentioned side, angle, side. And they don't have to go in order. You don't have to give me the step for the side, the step for the angle, just wherever steps they are. Now this was a fairly straightforward proof, so this one I'm going to have steps. 1 is where I said the side was congruent. Here's 2 where the angle is. And here's 3, the other side, reflexive. And that's my first proof. Okay? So let's go ahead and we'll try the next few examples, and then we'll come back.